So here's the main thing I want to talk about. When we started doing software engineering, we said, oh, it's engineering, so let's do the same thing we did in civil engineering, mechanical engineering. And we did the waterfall model. And it took us about 40 years until we came and said, well, that's not actually working because software has some things that are fundamentally different, right? Mostly how fast it changes. And we started with Agile. Now, a few years ago, we started doing data science and AI and model development. And the first thing we did was simply say, oh, look, just do the same thing you do for software development. Right? You can just do Scrum and do software and do, you should do testing and you should do configuration management. And let's see where that takes us. And the hope is that we take less than 40 years to identify the differences that are fundamental to kind of building models versus building traditional software. Because really there are some things that are fundamentally different when you're mostly building models. And this talk is about really 3 of those things that you need to pay attention to. So this is the first and most important one. Okay, this is the one thing you need to know when you're actually putting any machine learning or deep learning models in production. The minute you put them in production, at that point, they're going to be as accurate as they'll ever be. Okay, it only goes downhill from there. Okay, which means that in contrast to say, a calculator, right? So if you coded a calculator and you tested it, it's still going to work 5 years down the road. A machine learning model probably wouldn't. And it will probably actually start degrading much, much earlier than that. In some industries, it's going to degrade within days or weeks. So here's one example. This is from a paper at Black Hat 2017 that looked at a cybersecurity example, malicious URLs. And what they did here, they put 3 models in production, and they measured kind of their accuracy over time. They started in January 1st. And as then you can see, what happens is when you start, you can be very close to 100%. In terms of kind of how much you catch and the accuracy of it. But then you start degrading, and not only that, you degrade unexpectedly. Okay, so you find that then one day, a new attacker comes on board, and now you're no longer 98%, you're more like 68%. And then 2 weeks later, one day, you're 48%. And this happens across different models. And one of the main things that they concluded was, look, the world changes, right? The fact that you trained the model on a previous data set, and that it did extremely well in terms of whatever accuracy metric you chose and you put it in production, doesn't mean much when the environment changes. Okay, so that was kind of one classic example. And most people look at this example and say, yes, look, of course, makes sense, valid point, but this is cybersecurity. Cybersecurity is an adversarial environment, right? The moment you get better at blocking something, you have a team of attackers who are humans who make money off robbing you. And they also get to work in the morning and they start working around whatever it is you built. But this is a much wider problem. And here's another example. So this is a healthcare example, something that we've worked on 7 years ago around hospital readmissions. Okay, this is a kind of really popular healthcare machine learning example, and most researchers or companies do this as one of the first things because you can do this of the identified claims, and there's a real business imperative because Medicare is now penalizing hospitals who have kind of too many kind of unwanted readmissions. So when we did this at the time, we had huge data sets. We had really the majority of commercial claims that were filed in the US over a 2-year period. We had really good coverage of zip codes, of demographics, of ages, of gender. Everything basically that was commercial. And we looked at it and said, oh, this is a really easy problem. It's kind of classic supervised learning. We do have a representative data set. We can see who went into hospitals. We can see who was readmitted. So we have fairly clean label data, and we build the model. But what happened was very similar to what happened in the previous example, where within a few weeks of deploying a model within a hospital, the model started degrading. Okay, and when you talk to doctors, they tell you, look, this is ridiculous. Look, you're at higher risk if you're older, if you have a history of smoking, if you're diabetic, if you have other chronic conditions. Like the model does not change, right? The risk factors do not change. So the question is, what is going on here? And there's a number of factors. So one thing is that, healthcare is local. So the probability that my pneumonia will return, okay, is correlated to the probability that your pneumonia will return if we went to the same hospital. okay, because it's probably the same strain that we were not vaccinated against. Obviously, there's seasonality. Okay, my pneumonia will, or whatever the disease is, will act differently, whether it's summer or winter, okay, depending on weather. There are changes in the hospital, okay, and this is something people don't expect, because they say, look, we're here in downtown Boston, like the population changes. Sure, maybe once a decade you may want to look at demographic changes. But what happens is, look, you have one hotshot doctor moves from hospital A to hospital B, a whole set of patients move. Right? So all of the people with that kind of cancer move away, okay, with that type of cardiology problems or orthopedic problems. Okay, you add 6 more beds to the ER. You completely change the distribution you were seeing in production. Okay, you stop taking Medicare, right? You lose a whole age group. Okay, that happens often and immediately. Another thing that happens is just the impact of deploying the system. So, this is not a scientific exercise, right? The goal was, we deployed the system to identify high-risk patients, okay? So that, there was a team of people who actually followed with high-risk patients, right? So if I'm a, kind of frequent traveler, I come every time and you fix my blood pressure and I go home and I never follow up because, whatever, I can't afford the copay or I just don't, I'm going to be back. But now if you're actually sending nurses to make sure I took my medications, I follow up, I do my physical therapy, my risk is lower. Okay, so just by deploying the system, essentially you're breaking the model. And in reality, you have all of these things combined, okay, which leads to these beautiful messy results where really kind of, everything is okay. And then 1 week, it seems weird. And 3 weeks later, it seems junk. And 3-4 months later, really doctors and nurses just start ignoring the systems. Because you just look at the list of patients and says, well, this is obviously a joke, right? Because, I know the patients, right? This is not the correct list. Okay, and this happens really in almost every vertical you work on. So when Google published in 2015 an overview of kind of what they learned doing ML in production over a decade, this is a classic paper, really kind of required reading for everyone, basically, if you're doing if you're working in production. And one of the key things they found is really just this exact same fact. One thing they found across all teams at Google, whether they were doing search, they were doing advertising, they were doing spam, they were doing personalization, and they found this exact same thing. The world changes, right? So if you're returning search results for clothing, it's very seasonal. If you're doing it for for movies, for music, it's kind of celebrity-based, right, or whatever is hot right now. Political winds change. And this is kind of the main thing you need to know about, right? So you put a model in production, and then really you need to start fixing it. The other thing we've learned is that how fast this happens is not something you can fix technically. So it's not as if, if I'll have a smarter deep learning algorithm, then it's going to be less of an issue. It's much more a function of the problem. Okay, so if I'm dealing with cybersecurity, if I'm dealing with auto trading, if I'm dealing with real-time bidding, right, which are kind of real-time adversarial systems, yes, you may need to train your model multiple times a day, okay, which is what people do. Okay, if you're doing a facial recognition or voice recognition, yeah, you may be able to train once a year. Okay, and by the way, the issue there is not that people's faces change, but cameras change, right, about every 6 months or every 12 months. Okay, if you're in between, like if you're looking at for example, clothing, right, then you have kind of those, you have the fall and the spring kind of collections, right, and that's what you need to follow. Right? If you're doing retail, you have back to school and Super Bowl and Christmas. So what you need to do, what you need to know, is that you really need to pick the right infrastructure and implement it. Okay, and one thing to know is that technically there are solutions to all of these problems, and they are in use and they are fairly proven. Okay, there's active learning, there's master challenger protocols. You can just have a weekly batch retrain pipeline if that's what you need. Right, and there's all of those layers of solutions, and at this point, they're well studied, they're understood, they're in production in many places. And if you have solid kind of data engineering, data scientists, you should be able to tell you, look, here's how you do this. The key thing is really just picking the right one for your problem. Okay, which is really simple. If you don't need to retrain 10 times a day, don't use an active learning solution because you're heavily over-engineered. Right, you're going to have a system that's far more complex than you need. And on the other hand, if you downplay it and you rely on people to come in the morning and look at logs and see the accuracy and train, you may be way behind where you need to be in the marketplace. Any questions so far? The slides are online, yes. Okay, next. So, one really cool thing about software in the 90s was that you could kind of write it once and then you could sell 1 million CDs of the same thing, right? And software had this kind of zero marginal cost. So that was really fun while it lasted. But now we're in a different world. And what happens in the machine learning and AI space is that actually very often you need to build different models for different types of customers. And one good example is really the same healthcare examples we spoke about before. And the reason I stick to it is because this is kind of, healthcare is the one case where people least expect it. Right? Because I said, this paper from 1989, it has the risk factor. Those are the risk factor. It's been validated 34 times since then, we can just use it. Okay, which is nice academically, just simply does not work in practice for a variety of reasons. Here's one example. Here are some of the, I think the latest model is still in many ways the most widely used, at least in the US. It was published as a paper in 2010, and there were a few updates since then. And when the NHS tried to test that model on an older UK population, they found that the AUC was kind of in the mid-50s. Okay, which is a polite way to say this is complete junk. Okay, basically what they found is that if you just ordered patients by age, you would get a more predictive model than when using this. Okay, and when it came to the original study authors, they said, yes, of course, we know, we wrote it, it's in section 5 discussion. Okay, because this is like any predictive model, it's tuned to its own training data. The training data here was mostly middle-aged women, from Ontario. So if you apply this to an equal population that's over 65 years old, why would you even expect this to work? Right? I mean, it's just, it's not the same people, it's not the same diseases, it's not even the same gender, right? Why? Why? Okay, and really it's as simple as that, right? You just need to know that when you apply your model to different types of people, and you probably need different models because different features will work. So when you are building your own product, what you need to remember is that you're not necessarily ready for your next customers. Okay, and this comes as a huge surprise to CEOs and product managers because they're used to software. And one thing with software is like, if I build it, I can sell it. Okay, that's an assumption people mostly make. Okay, what you need to know is this is not always the case. Right? The fact that you actually have this deployed in production for 10 different banks doesn't mean that you actually have running models for the 11th. Okay, so it's another example. It's a project I worked on a few years ago. A natural language processing examples. We're trying to do automated clinical coding, and these are 2 different outpatient radiology clients. Okay, and outpatient radiology is the simplest specialty to do this kind of automated clinical coding on. And this was very typical. We had about 25 kind of different customers at the time. These are all kind of nice one-page reports, and the goal was to know what was done to this person. Was it an X-ray? Was it a CT? Right, of what organ, and so on. And really would move from a model that was 90% procedure, 90% accurate, 90% recall, to a model that was 50% precision, 10% recall. And just to explain, a model with 10% recall means that 9 out of 10 times you just don't show anything, right? You don't make a guess. 50% precision means that when you make a guess, you're wrong half the time. Okay, so from product perspective, like a product manager would tell you, just turn it off, right? It's just like, please, right? You don't even want to explain this. Okay, and this is when you're doing really well on other cases. Another example, this is also another paper, and the links, by the way, are in the paper, in the slides, if you look at the slides. When you look at cybersecurity, and this was also a malicious URLs example, when they looked at training models on one set, basically testing them on other cases, other data sets. And you see that you move from, you can get anywhere from 84% to 51% to 15%, depending on basically how lucky you got. Okay, and intuitively, this makes tons of sense, right? You can see this in banking. Right, so you cannot assume that people in California and people in Florida and people in Barcelona bank the same way, in the sense like, and it comes down to culture and conventions. How do people think about money and loans and the priorities? Right, which music they prefer, Okay, how do they shop? How do they play video games? And obviously healthcare as well. One question that people keep asking, this happens a lot, especially if you're selling AI. You get asked, how accurate is your model? Okay, so if you're in sales mode, my model is extremely accurate. It's 98% accurate on this benchmark data set that you probably know about. Okay, and you can always kind of, you can always answer that because you can always fit your model to whatever. But really, it's the wrong question, right? And you should know this both as buyers and sellers of these kind of models. Right? The real question is, how accurate are you going to be on my data? Okay, or more pragmatically, how fast can you get to that level of accuracy on my data? Okay, because especially if you're in a business scenario, a solid assumption is that whatever, if you trained your model on the, last 10 years of Mayo Clinic data, no, it's not going to work here in Boston. Okay, and it's not even going to almost work. Okay, so what it means is that you need to understand kind of what's the right question when you're buying these or simulating the software. When you are building them, what you need to think about is that you'll probably need a software engineering infrastructure that can train and support a large set of those custom models. Okay, so if you have 100 customers, you're probably looking at several hundred models that you may need to deploy, measure, and operate. So far we spoke about the fact that yes, look, you need to operate and measure and kind of keep your models accurate in production. You may need quite a few of them. The next piece of great news is that it's actually really hard to know when you're improving something in production. So usually kind of the classic technique is I have this model it's running, I have this new model that's better, and I do some kind of A/B test to see if my new model is actually better. Okay, and the main thing to know here is that it's actually extremely difficult to do this well in practice. And here are some examples. This is a great story from 2014. I'd recommend you read it. It's technically accurate, and it's also just well told as a story. It's a nice long blog post. Who here is familiar with Optimizely? Okay, Optimizely, it's a great product. It automates a lot of the kind of web A/B testing, right? So if you want to know whether the website, the button in red will cause more people to click it than the button in green, you can have two versions. It's really like live on the website, point and click kind of thing. You can say I want 80% of the traffic to go here, 20% to go there, and Optimizely manages that and makes sure that it keeps sessions, right? So if I click back on my browser, I still see the same color because it's always the same session. So you have good user experience, and it obviously collects all the data and calculates kind of hypothesis testing and tell you, after we have enough data, which model performs better. And this is a case study about a company who's been doing exactly that, to look at a revenue lift. And there are two kind of parts of the story. The first one is about the fact that, yes, they had a case, and that's a case here, when they basically had a 100%, look, this model is going to bring you much more money than the previous model. And when they deployed it, say they only saw 10 to 15% of the actual lift, which was very surprising. But the problem was that what they did then was they actually repeated some of the older experiments and simply could not reproduce them, okay, in any way or shape or form, right? Which brought them to a much bigger question of what the hell are we doing here? And other than a specific story, the point is this is basically what happens to everyone. It happened to me, but more than that, if you look at Microsoft, Google, Amazon, Facebook, they all have the same stories and the same teams. And basically, I'm yet to hear about one company who's been able to get this right. And it goes all the way from Facebook, who 5 years into it say that no, we actually miscalculated reach numbers, right? Which is kind of the one number that the customers actually care about. And definitely to smaller companies where it's very hard to actually get these things to work, right? Because you can say, oh, this is the methodology, this is the best practice, we do A/B testing. It's actually very hard to get to a point where you are consistently improving your metrics. And here are some of the reasons why. So this is Alice, I think she's now at Amazon. She wrote this when she was at Day2 at the time, about some of the things you need to pay attention to. Okay, and the problem is not with the product like Optimizely, right? The problem is, if you remember, first year statistics, when you do those, t-tests or f-tests, there's a lot of fine print, which you really need to pay attention to. Okay, so things like really are we confounding different types of tests? Are the variances finite? Are the variances, do they have the same distribution? Okay, are they equal? Should we do a one or two-sided tests? Okay, and these are kind of really important concepts because, for example, if you have a metric like number of sessions, okay, then that obviously grows with time, right? Because just the more times I log into the site, I have more sessions. If you look at sessions per day, that metric actually does not increase with time. Okay, so you have one metric that has a variance that kind of grows over time versus one metric that has a finite variance. So you need different tests for them. Okay, which means that if you go in with the defaults of all of those tools, you're going to see very different results. And the nice thing about statistics is that if you make a mistake, you still get a number, right? It's like, nobody tells you that the number is completely meaningless kind of in real life when you actually test it, but you get a number, right? It's not like it doesn't fail. In the specific example of the optimizedly example, the issue was that they did a two-sided test while really they should have done a one-sided test. And I remember when I first read this, and I had quite a few data science teams at the time, and I remember thinking, I don't even know whether whether we're doing one or two-sided test right now, right? Because it's just kind of one of the things that you almost don't think about when you're thinking about your feature engineering, your classification, right, and your metrics and your measurement, right, and integration efforts. So it's kind of one more thing to the list. Microsoft has a team that's been working on this, as in having several hundred people who's been working on experimentation for about a decade. The person who's leading it is Ronnie Kochavi, who's also done the same with Amazon before. In 2012, they published a great paper called 5 Puzzling Outcomes Explained, which tells basically 5 stories about cases where they've seen different numbers, which made no sense, they could not understand. They've done, have a set of PhDs who did an investigation on what happened and learned from it. Okay, and really the key thing about the paper and kind of others that came from Amazon, from Facebook as well, is really just, yes, it takes several years of hundreds of people working to uncover some of those issues and understand what's going on, and then it takes time to maintain them. So here's one example. In this example, let's say I added a new feature to the site. So I added, oh, look, I have this new widget. People who bought this also bought that. And it's really cool because it shows more things, and you click on more, and you have longer sessions, and you're more likely to buy. Okay, so I deploy my feature to production, and it goes to 20% of the traffic. And immediately the next morning, I show up to work, and I come and say, okay, show me, are we getting more clicks? Are we getting more revenue? What's going on? And you start building those graphs where day by day, you look at kind of what's the cumulative effect of my new killer feature, right? And then either it works or it doesn't, okay? And then people mostly have 2 rationalizations to this. There's the primacy effect and the novelty effect, okay? So primacy says, look, I know it's not going so well now, but it's because people don't know about it yet, right? So most people still use the old habits, right? And it's gonna get better, right? The novelty effect is the reverse. Look, this is the new bright button. Of course, everybody's clicking on it, but it's going to relax. Right, in 2-3 weeks, it's going to go back to normal, right? So don't worry about it. In reality, usually what happens is none of these effects. Usually what happens is simply you start, with some kind of variance, and you see either, an improvement or the aggregation, and over time you go back to 0, which is really just regression to the mean, okay? Because really this is one of the most misleading visualizations in statistics. Right? Because at the beginning, in the first day or first 2 days, your sample size is so small, right, that really the variance is far, far bigger than it is on the 4th, 5th, or 7th day. Okay, so really in the first day, if you're anywhere from -2% to +2%, you'll find you're well within the standard of error. Right? It's basically like saying, oh, I'm doing a survey for voting. It's like, listen, I spoke to 5 people. They all said they're going to vote for the same person. Right? What do you think it means? Right? The answer is, look, it probably means nothing, right? It means very little before we spoke to enough people. Okay, and the real problem is that people come in the morning after they deployed something and actually look at stuff, right? Which is a very social thing to do. And really what you need to tell people, look, really in the first 3-4 days, you just don't look at it, right? It's complete noise. One of the ways to do this was actually do AA testing. Okay, AA testing in practice, when you do an A/B test, you come and say, here's the site with the green button, here's the site with the green button. It's the exact same thing. 80% of traffic goes here, 20% goes here. It's the exact same. Okay, and the reason to do it is, first of all, to check for bugs in your data collection software, okay, which you may find. But really, the main reason to continue with it a year and 2 years later is really for the social education. Right? That people need to understand, yes, an AA test, oh yeah, you're going to see huge variances in the first few days. That's what you're supposed to see. It takes time for it to regress back to zero. Right? And if you're doing this several times, yes, you should see different results. Okay, this is how statistics works. Okay, and this is one of the things that definitely, I mean, I've seen working, because the other thing that happens here, even if you do the case study and show this to everyone, it takes 6 months and then they forget, or other people come. So that's another thing that you want to make sure you cover. So to conclude, here's the main thing to pay attention to. Right? So one thing that's really different with data science and machine learning project is that really after you've put the project in production, oftentimes that's when the real work really starts. Okay, you need to see how you build feedback loops, how you measure accuracy, okay, how you know that we actually 3, 6, 12, 18 months into it, you're still doing well. You need to build an infrastructure that enables you to support multiple customers, which will often require different models and definitely require different measurement schemes. You need to think about your development process. Most importantly, you need to set the right expectations with your customers, with your managements, with your engineers as well. Okay, so data science is usually you need your senior data scientist after you're in production, not in the beginning. Right? So building a model based on historical data, that's homework exercise. Okay, actually being able to do A/B testing and keep a model running accurately in production, right? That's where you need your smartest people. Okay, part of it is really thinking about what your profit margins can be. Right? It's really how much work do I need to do for my next customers? How fast can I actually make my next deployments? Okay, and this is where a lot of companies are struggling right now. Okay, where they're actually losing money on each and every deployment. And the other thing is, if you're really scaling, forget the data science piece. There's a software engineering piece to enable you to actually serve a large number of models at scale. Okay, so that's what I have. Thank you, and I'll take questions.